All right, good morning, everyone. Thank you so much for being here. We are Group 3, and we're here to present a plane that we are designing for Aerospace Design 2. I'm going to walk you through our agenda real quick of how the meeting's going to go. First, we're going to go through the mission requirements required for the project, followed by our personal objectives and goals. And then I'm going to talk you through our design process and how we went about our stability analyses, and then catch you up on where we are currently.
So we have a few mission requirements that are involved with our plane. I'll be talking to you guys about some of the physical limitations that we have for our actual aircraft. So we have a maximum length and width and height that our plane can be, which is basically an 8x8x8 foot cube. And we have to stick to a limit of 55 pounds, which we're not really getting anywhere close to that. But yeah, and then it has to be powered by something electric, so nothing like gas or anything of that variety. We need to use propellers and blades, as well as battery packs that can exceed 100 watts.
So obviously on to the part you're expecting is the test flight. In our test flight, our aircraft is required to complete a roll and takeoff within 40 feet. And it is required to only use the batteries on board. Once in the air, our aircraft will fly 500 feet to the first marker right here, where it can initiate the first turn and begin following the course around for 3 laps. In the process, it needs to remain in the field of view of the pilot and also not drop any components during flight. It'll finally return back to the tarmac where it'll initiate the landing sequence. And then in landing, our aircraft must not sustain any damage or that flight will be invalidated. And the aircraft is able to run off the runway if needed.
This is a piloted
RC pilot.
So we have some overall objectives. Obviously, we want to meet the given mission requirements for the class, but also our group wanted to tack on another objective to design aircraft with surveillance and air photography capabilities. We kind of just saw this was like a growing need in aerospace in general for both military and commercial applications. And then also to design an aircraft with modularity for a couple of different reasons, mostly for manufacturing reasons. We're doing a lot of 3D printing. We want to print so much at a time, but also if we make any improvements as we go for design. And then before I show you our overall model, we had a couple inspirations when designing this. The first being the B-35 here. This is mostly, we had a lot of comparative like parameters and stuff from this plane with the stability analysis and everything. We think that's mostly attributed to how many detail ours does as well. And then the MP9 Reaper surveillance drone was just the idea. It has the same objective as what we want to accomplish with this plane, with the surveillance and everything, and the pusher prop. And then here is our CAD model. This is just a reference image before we start breaking down the individual components so you can see the full complete model. I do want to note though that we ended up going with the pusher prop for reason for the camera. We didn't want the blades interfering with. And then, well, to our design process, it was split up into 3 different phases. In week 1, we designed the wing, and we came up with the first initial estimations of parameters that will be explained further. This was mostly used to make other design choices later on and for comparing to different actual models. And then the second week, we did design the fuselage, propulsion system, and landing gear. And then to wrap up our design research, well, you're always designing, but to wrap it up, we did the tail design and stability analysis and compare them with different aircraft.
So we started off our design mainly looking at the weights, and the way we approached this was we looked at similar RC aircraft. We looked at the kind of payloads and electrical components that we'd have to carry, what kind of structures we need to support those. And we arrived on about 4 kilograms for our target weight. And from this, we used some basic MATLAB codes to calculate wing loading, using the wing surface areas and the weights, and using XFLR and some airflow tools for the airflow we're using. We found our thrust to weight ratios, lift to drag ratios, and our coefficients of lift to drag. And then using a MATLAB code, we also found the cruising speed that we would be flying, the targeting during flight, and the stall speed.
So what do you want out of a wing? You want a lightweight structure that is very good at bearing the load that it is required to. We also wanted to incorporate some similar parts. So by this we mean when actually assembling the plane, we don't want to be looking at the connector for stage 7 of the wing versus stage 6 and then stage 5. We wanted a structure that is pretty uniform. How we achieve that is a lightweight PLA 3D printed core. We added carbon fiber spars for support along the span of the wing, as well as a carbon fiber layup on the skin. We'll explain that later, and we've also got a sample. We have chosen the NACA 4412 airfoil. This we found to give us the best balance between a high lift coefficient and a lower airfoil moment. It has a very good efficiency at our target Reynolds number operation. We also wanted to minimize the wing area and specifically the span of the wing for the model that we wanted to make. For the design itself, we have a wingspan of 1.68 meters. This would be approximately 5.5 feet with a taper ratio of 0.8. We found this iteratively after trying to optimize our efficiency and minimize our bending moment. Our root chord was 0.216 meters or 8.5 inches approximately. And then for our alignment, the chord ball section was made straight to reduce the actual twist within the wing and also help with the way that we wanted to connect it to the fuselage itself. For our design, the inspiration behind adding the carbon fiber on the skin, we have found several examples of people who were doing this with their homemade models to increase the structural integrity of the part while minimizing the weight. Here is a cross section of one of the wing segments. You can see in the view here, we have 3 printing spars going along the entire length of the wing. 2 of these will be used to house the carbon fiber rods, such as the ones that we have there. And the middle one will be used to run our wiring. We have also optimized the rib at the base of each segment and are working on strengthening the end section.
So some of the overarching goals we had for our fuselage design was obviously we wanted a efficient, lightweight and strong structure. And we wanted to make it out of 3D printed PLA for ease of manufacturability and letting us rapidly iterate designs. The way we achieve this is we have a design that has internal bulkheads and stringers along the fuselage, and the places where the wing and tail connects have extra strengthening because that's where most of the loads are going to be experienced by the fuselage. And the fuselage, which is 4 feet long or 48 inches, is split up into 6 individual 8-inch sections. And each section has an access hatch on the top side that lets us access components and assemble the fuselage.
So here's a more detailed visual of the fuselage. You can see the different sections, the connecting components and access hatches. The entire length is 4 feet. We got that just from one of our aircraft design textbooks we're using. Use a fixed wingspan to calculate this 4 feet. And we started off with a rounded square shape at the beginning, and it tapers off to a circle. The 5 inches at the widest and the 2-inch diameter at the end. The square shape is mostly to have space and flat surfaces for all the mounting features we're going to be doing, like the cameras and the landing gear that we elaborate on further. And then the circle at the end is to securely mount the rotor at the end.
So here's a section view of the internal structure. And you see these bulkheads here are placed approximately 8 inches apart on each section. And the reason for this was that our 3D printers have an approximate max print height of 8 inches. So we wanted to accommodate that. And the way it's designed is that each bulkhead, or each section is split at the midpoint of the bulkhead. So when we print, both the top and bottom have contact area for fastening them together with these fastening holes here. And the hole in the bulkhead allows for both saving weight on that and getting the support structures out of these sections by stop printing for that top bulkhead. And the bulkheads are all connected by 4 equally spaced stringers, and these serve the purpose of transferring the bending and compressional loads from the relatively weak skin to the bulkheads. Actually here, the tail of the wing and the tail, they're both connected to the bulkheads for extra stability. And on the Middle of them are two tubes that the carbon fiber spars will run through. And hose clamps will be used on these tubes to secure the spars in place. And each section also has an access hatch, as you can see, and like I said, that lets us access components like the battery, assemble things like our landing gear, and then just assemble the fuselage.
And I'll walk you through our propulsion system. So our propulsion system consists of the battery, the electronic speed controller, notice ESC, the motor, and the propeller. So starting with the battery, we have an HRB 5000 mAh 1450C battery. This was chosen for its high power and long runtime, which would be great for surveillance. Moving on to the motor, the right side of the screen. This was chosen, this motor was, I used it. The avian motor, the 12,000 kilovolt motor was chosen as it meets our thrust requirements that were discussed in the general plan slide. The electronic speed controller in the top middle right here was chosen as it was recommended to be compatible with the motor we selected. In addition to the typical characteristics of an ESC, like with optimizing performance and safe flight, this one also allows for thrust reversal, which will help us slow down during landing. And lastly, the propeller, we chose to put one two-way propeller at the back of the plane. Next, I'm going to walk you guys through our landing gear design. One of the big considerations for us was the fact that we are in a short plane. Because of that, a tail dragger landing gear condition pretty much became infeasible because of the fact that we wouldn't have that right ground clearance with the propeller. But we wanted to do a tricycle landing gear formation for the ways because of the fact that it maintains the center of gravity in front of that main wheel. Thus, upon landing and while taxiing, you have better control of the plane. For our nose landing gear, we externally purchased a single wheel on the rod to make sure that we had a good quality part. For our rear landing gear, however, we will be making our own carbon fiber leaf spring. Lastly, we decided to go with rubber tires as they are much more durable than foam tires upon landing, and also they provide better ground control. On this slide, you can see pictures of the nose landing gear and designs. For the rear landing gear, one of the highlights that I want to you guys is the fact that our connection site for the landing gear to the fuselage allows for flexing in the flat section of the landing gear, which will allow the system to have better spring. Additionally, these two circles here are rubber O-rings that will improve the damage of the system. For our tail design, we were favoring a detail over the conventional tail. This helps us with our pusher pop idea, because the necessity of huge drag, and get the look of air for the tail. Additionally, the detail offers the benefit of having fewer surfaces to make it accurate, so that will help us out with time and overall profits. So after deciding that we would do the detail over the conventional tail, we were able to get the tail dimensions by considering the functions the detail would have to perform as both a horizontal and vertical component. So that ended us with a 15-inch span on each airfoil, and we chose a NACA triple airfoil with a 6-inch core, as well as a high heat of 30 degrees and a taper of 0 degrees to make the lock.
So in the CAD design for the tail, we presented it in the form of connection slot. If you can look at the connection here, it allows for modularity where we can replace or even upgrade our wings or airfoil at different upgrade intervals if we need to. In the rear is a motor unit, and on the left is on each side we have the airfoils. And on the other side is the different unit for the airfoil. If you take a closer look, this is where we want the air slot. The sides have 2 circular connections for the spars that will support our airfoils. And we have another view on the other side where we can have a more detailed view of the spars. And we also have additional holes that we allow for electronics that we can add wiring for one for serving and also for LED lights that we have for. You can see there's still a lot on stabilizer here. If you look under the motor mount, not the motor mount, the servo mount is visible, and it allow us to attach force or movements of the rudder blade as well. And we have a section of view that also shows hollow inside for wind concerns. This is just another view of force. This allows us to have movement on mountain servo arm. Therefore, and we have a more detailed view where we can see the servo and interaction between the rudder and as well.
So before our first test flight, we wanted to kind of gauge the flight characteristics of our aircraft. So we performed a static and dynamic stability analysis. Starting with the static, obviously our goal was to get the three coefficients, roll, pitch, and yaw moment. And as any good CFD or simulation group would do, we started by running an XFLR simulation to get our three coefficients, but we also made a MATLAB script to help verify those values and make sure that there were no issues in our XFLR simulation. And obviously moving on from that, just to kind of make sure that our aircraft in terms of stability was where we wanted it to be, we compared the numbers we got from both of those simulations to historical aircraft and their stability coefficients.
So once we knew that our plane was able to fly and stable, we also did a static margin analysis, which is basically a non-dimensionalized value between the aerodynamic center of the aircraft as well as the center of gravity. And what this kind of does is it gives us a little bit of a margin to allow our plane to be easily more controllable, which is pretty important when you're thinking about some of the raw calculations that we have from our plane. You know, a lot of times with, for example, this pitch moment versus alpha, having too many things that will overcompensate in stability will actually cause the plane to crash. So we don't want certain things to happen too quickly. So for example, if there's a wind gust, we don't want the plane to overcompensate and then end up crashing in the opposite direction. So static margin helps with some of those things. It also as well lowers our cruising airspeed, which allows for more controlled flight. In addition, these are some of the values that we got from the simulation. So this is a value that we got from MATLAB as well as the value that we got from XFLR. Some of the most important things are just to indicate that the value is negative, which is what means that it's stable, and then the value outside of that tells you how much. And then those things, yeah, are comparable. These numbers that we have are comparable to those planes that we were closely comparing to for the detail as well as the surveillance threat. So, yeah.
Where are you falling? Sorry, where are you on this chart?
So this one, for example, here's the Bonanza. So we got a value of negative 0.06. So, you know, we're going like close to things like that. So for example, the detail of the Bonanza.
And if you go back to the last slide,
Yeah.
you can also see that we're pretty similar in both roll and yaw,
Yeah.
which obviously our tail is going to be a pretty high contributor in those areas, which is why we wanted to use the D35 Bonanza as a good comparison for aircraft. And then moving on from that, we also did the dynamic stability analysis. So we started by, running another XFLR simulation to get the eigenvalues for 5 different modes. Starting with the longitudinal modes, we analyzed both phugoid and short period. The response of the short period mode was as expected, pretty quick. You can see, damping out in about 0.6 seconds with pretty minimal oscillations, and the phugoid mode also pretty on par with what you'd expect, a lot longer time to dampen out, but also some high oscillations, both stable and converging, which is good. And then onto the lateral directional modes, we analyzed Dutch roll and roll subsidence. We're also focusing on the spiral convergence as well. In terms of Dutch roll and roll subsidence, both converged, almost no oscillation in both of them. And in terms of the spiral convergence, we got a positive eigenvalue, implying that we're on the stable side of that convergence. So there's no risk of any, uncontrolled roll that kind of rolls out of into a spiral turn, whatever, out of control.
So past couple of weeks, we've started to manufacture some test sections for our fuselage. We've done this just test fit parts, see how our structures perform in real life. Some lessons we've learned from this are that our initial structural design was a little bit too strong and too heavy, so we revised it to make our bulkheads a bit thinner, smaller.
We also began manufacturing the wings into pre-test sections, and we did run into challenges with translating the cabinet level into the slicer into the 3D printing. As you can see, that caused some gaps, some swinging, some weak points in our test sections. So we revised it again to make it optimized for 3D printing, and this is the test section that we got. As you can see, we did one layer of lightweight PLA on the outside, which was not as strong as we wanted it to be. So we did do a carbon layer test on that section. It is right here. And even after the carbon fiber layer, we decided that we wanted to increase that thickness on the PLA just to give it a little more extra strength. So moving forward.
So our current work the next couple of weeks is to continue printing parts. And for those parts that need it, we'll do layups. After seeing the manufacturing results of these parts, we can then optimize our designs. With those optimized designs, and of course, ensuring successful manufacturing, we can then assemble those parts to create a complete aircraft. With our complete aircraft, we can then prepare for our next goal, which is test flights.
Thank you so much for coming, guys. We have included all our names at the top of the slide, so that if you have any questions, you can direct the person that talked about this.
I know there's gonna be a quiz.
You open up Canvas on your phone.
It's Canvas. Oh, okay. Okay, so as a structures guy, the wing is interesting. That looks like it's a layer of carbon fabric wrapped around a plastic printed airfoil shape. Lightweight. Okay, yeah. How is that cured? I imagine putting temperature is gonna be hotter than plastic. Actually, the interesting part about this, when we did it, we actually applied it epoxy to the surface first, and then we applied just one layer of the carbon fiber, and it was just naturally cured. Okay, so it's like a room temperature cure. Yeah. I mean, that came out. I mean, I don't have a ton of experience on parts, but I know they tend to get wrinkly. That came out very nicely in the bag. I guess that's maybe a functional evidence. I wonder what the trade was, because I mean, you can feel it's still, fairly flexible, and maybe, maybe that's good for a plane that, There's one thing, part of it was damaged. Yeah. During but yeah, we did address that by making it a little bit thicker to support. So some sections are much. Oh, yeah, definitely the spars are definitely bigger and out here at the tip where you got the curvatures stabilizing. But I'm just kind of curious about like the trades between carbon wrap versus just adding additional plastic. Like if you're talking about bending stiffness, right? A single layer of carbon fabric is not particularly stiff because it doesn't give you a lot of moment of inertia, right? Whereas, I mean, it certainly is going to get stiff faster than adding plastic, but it's adding compressive. Right? So I'm curious what the trade was between the complexity of adding carbon versus just adding another layer of plastic to the.
So we also saw increased gains in stiffness. I think over here we have it. We did a layup which was not as successful. Over here, with all 4 segments attached, which are which is like the first half of the wing. And once all 4 segments were attached together, that did increase the stiffness, as well as we had other test prints with the regular PLA. I mean, no, just go over here.
And the other issue with the lightweight feeling, it's very, it's not too firm. So if you want to get increased rigidity, you'd have to think, thicker.
Yeah.
And then I think from what we've tested, applying the lightweight feeler and then the carbon fiber is reasonably a small increase. So it doubled the size of the lightweight feeler, but still for our target rate, it is within the range of what we want. But of course, I look be able to continue.
Yeah, so sorry, or in terms of the prints, how our evolution went, we first tried one with regular PLA. One thing that we were struggling a lot with was the thermal, because of how the G code actually lay up the PLA on the skin and the ribs. We got some thermal contraction and the skin was breaking up. We were also trying to deal with how to attach different segments. And so what we've been toying around with some ribs, because we did see a lot of flexure on the skin. If you look over here, this was a different PLA, so the one that's right there, that one has additives to it. It printed at about, that's like 32 grams, so like 80% of what regular PLA was printing. This one was printing at about half the density, so it was 14 grams. It was almost paper-like, pretty good material, but it gave us much better performance at the juncture between the ribs and the skin. And so we rolled around with that. What we've been also trying to do is implement some ribbing to actually connect the segments and not just rely on like the spars going through. That is a current progress with dealing with the tolerance.
And we have one more test we're about to conduct. It's, as we're speaking, it's actually drawing right now. We're going to use a more applicable for brown material, the carbon fiber nylon and filament. So that's we'll be using, we're starting up today. So that is actually drawing a lot. So it's also ongoing testing.
And then on slide, I think it's 15. Maybe jump around. Yeah. So I'm looking at your bulkhead attachments, right? And those holes look to be in the center of acreage. Right, so and when I say acreage, you know, like sort of big, long, open expanses. I'm wondering why those don't wind up closer to like the longerons, which would kind of give you a stiffer load path for those for the loads being carried up passengers. I think that is one of the things we advised in the second phase we made. They just cut out the strings were all say decreased. Yeah, well, I'm thinking. Sorry, right? So like, if I fully understood your. Yeah, so like your fasteners, I assume this is like a. Yes, it's a full section. Yeah. So to me, your fastener wants to be kind of tucked in near the boat, right? Rather than out here where when the fuselage tries to bend, right? It's going to create like this big moment that's got to carry through probably the cap of the bulkhead surface into the fastener, right? Whereas if the fastener is close to the longeron, right, that's where all of that longitudinal tension force will be, and it'll drive right into if you have a fastener on the side of the longeron, that's where the load's going to go, right? So out here is like inefficient structure, whereas tucked in here is better load backs, right? So that's from a structure's perspective, that's another step. That's definitely like a really good suggestion. But I mean, obviously there are other considerations, right? You've got to
physically be able to
Yeah.
get your hands or a tool in there
Mhm.
to.
I think
fasten something.
the main reason why we didn't do this was just for zip assembly. Like accessing something down here might be tough to access. That's just.
Yeah, because you're coming in
Space
from the
for
top.
it.
Yeah.
And we also did determine that these are relatively stiff enough that with fastening washers, it does kind of, it is stiff enough to spread out that force. Once we test some more, I think, we could definitely try something like that in fastening location.
Yeah,
So
I
that
think
gives
you
us
could
better-
probably
better
thin out
structure.
some of the two different bulkheads.
Yeah, this was our first iteration of it, and approximately half of this was taken. So I was able to make it considerably lighter after our first test.
Yeah, and then you said the wind spars would come in through those tubes.
Yeah,
And then we put in like a hose clamp on the end just to prevent them from.
so, yeah, the hose clamp is just gonna go around this tube section.
Oh, is that a flexible?
Yes, it's just I think you can probably see it there, it's just, there's a little cutout on it. It should be able to break down.
Yeah, so you get front by the rod, and then I guess it's slot. Gives you this components. And here you've got them come together, right, which is great, that's where you like. Wrap it rather than the skin. Up here, am I seeing that it's cut?
It does go all the
And
way
so-
through in this
yeah,
thing.
Going all the way
Yeah.
through, it's continuous.
So it'll connect through both the wings.
Yeah, when you go back to the other side, am I seeing like a little gap at the root of the wing? in the fuselage? What's,
Sorry,
is that just a different shade of?
You mean here or?
Yeah,
Here?
Like this part,
yeah, is
That's
that
just it,
like a
that's just
surface?
yeah.
Okay, so it's like just.
Yeah, yeah.
It is,
Also-
it's physically part of the surface.
It's
Yeah, yeah,
also
it's
part of
always
this
there.
as well. So if you look, it's a part where it will go in.
Oh, okay.
To make it modular as well.
Okay.
That way, if we needed to change this profile, we wouldn't have to worry about interfering with this. So you've got some ability to react moment, through that connection as well, in addition to.
The spars are gonna be doing most of the heavy lifting.
Yeah.
Depending on
Yeah, okay. It's like that. Sorry, and so away from stuff that I know how to talk about, using stuff like that. So you said you've done some XFLR simulations, simulation. I don't know what XFLR is. I know what MATLAB
It's
is.
basically a aerodynamic analysis software, so you can upload your airflow shapes, wing geometry, and it'll run like some basic, airflow theory calculations or something.
Yeah.
And you can get stability and eigenvalues.
And you visualize the stability motion. So,
Just give you general parameters like coefficient of drag.
okay, so you've got, you entered your airflow data, your weight CG and stuff, and see what's the law. Get results. And you said you did some MATLAB simulation.
Yeah.
Right. So saying to me, oh, I did MATLAB simulation, that's like, oh, I did, Python simulation. Okay, that's the
Yes.
framework you did it. What did you do?
So essentially, I wrote a code to basically use all of the equations in terms of stability. So obviously, the lift and the moment arms that the lift is acting from, essentially the isolate longitudinal, lateral, and directional stability, and calculate those coefficients accordingly. So if you go back to, well, this is one of them, one of the 3 slides, we just used that coefficient that I calculated in MATLAB using, our textbook equations essentially.
So we have, from my perspective, and my advice to you would be, tell me that's what you did. Don't tell me you did MATLAB, right?
Yeah,
Because to
understood.
me, I want to know, okay, I've got, and I've talked about this when people defend all the time. Thank you. The message is getting through. It's taking a few semesters to get through. When people do a FEM, right, I say, okay, where do you, say, how do you know that the FEM is not garbage? Yes,
I was
and
gonna-
so what you've done is use MATLAB to do.
Exactly,
Right,
correct.
that's what I
Yeah.
want to hear, right? That, like, tell me we validated the XFLR results with hand counts using equations from the standard textbook from, Lewis, Anderson, whoever else.
Yeah.
That's right, not that it's.
Okay, understood.
In addition, we also wrote, within the MATLAB the Midterm theory, we apply that, we did the calculations that not that that's a efficiency factor, which we also use to plug into the other calculations as well.
That's how we optimize, like, for example, paper ratio and all that. I think we added like 50 different elements to our lift line theory.
Yeah, one of the advantages that we had with the XFLR5 software that basically let us run the simulations with the airfoil is we could actually input basically very closely the exact like shape of our wings, so for our detail and our actual wing. And so that gives us a lot of flexibility in terms of also running iterative processes of, okay, if we change this very slightly, like the wingspan from 5.5 feet to 6 feet, or if we change the dihedral angle, if we change the twist, like how is that going to affect the way that our plane flies? And so that software is very helpful for us to do that and to model those things, in addition to also doing things.
You guys are building a plane that's flying at, I would guess, in the neighborhood of 40, 50 miles. Right, yeah, 19 meters per second. So that's like Mach something. Right? Yeah, so I've got like all of that, right? Like the F-104 doesn't tell me a lot about like what I would expect out of performance of your vehicle, right? So yeah, like
That's why if you go on to the next one, so these two, we compared mostly to the E35 Peninsula, which is right here. It's Mach 0.2 essentially. We're probably a little closer to here, but in the exact same range of static
yeah,
stability.
so give me that though, right? Like give me information I can use to say, oh, this is comparable to our inspiration is a V35, which is pretty flying closer to it. Thank you for the but even other like flying bus here, that's the comparables rather than something flying beyond space. That information doesn't like add a whole lot.
Thank you.
Yeah.
Thank you so
Thank
much.
you so
much. Very valuable.
I have some questions. So first, yes, it's great that you don't have FDA, but where is structural issues? I mean, I didn't see anything like it.
Yeah, we didn't include the.
Why?
calculations in the
Let's
first
talk
decision.
years. Why? I told you guys.
I'm okay with it. No FEAs.
I would
It's-
prefer in these 30 minutes to show a little bit hand calculation, like to prove it's safe. So I do believe like stability analysis is very important. I also believe structural analysis is awesome. Page 14. Yes, about this one. So you have so many openings on top. I mean, is that really necessary?
Well, we have a lot of components, like with all the camera stuff we're going to add and like make sure landing gear is implemented correctly, like we just don't have access like from the top, because we want so much space.
It's like every time you open something for structure, you weaken structure.
Also,
I-
we did test this by one of our test sections. We actually cut out access hatch every time. We did see that cutting out the access hatch on top didn't affect the structural strength of it that much. And the way we designed the access hatches to go on here is they're basically going to kind of rest on top of these top two stringers, kind of like a redshift and Velcro, so they should be very easy to remove and take off. They don't really impose too bad of a structural load decrease on them.
So
Hopefully better
if you design your longerons to be your like structural member, right? And particularly in a fuselage, where the bending is going to be down, right? If you're doing live media or something, make it but for the most part, right, you're pulling positive G's, so your fuselage is bending down, right? So you're not putting compression in things, you're not wanting to buckle things at the top. So to me, like if you're gonna have them, in the top is the right place to do it, right? If you're doing the wing, then the right place to go on the wing is the bottom section, right? Where you're primarily in tension, you're gonna be buckling. So as long as you're able to, again, back to structural analysis, if you're able to show good, assuming that all your load is going through the longerons, the slings, whatever you call them. Then I think it's okay. And nice generous corners, right? So you're not like driving Z-road, although I'm not sure how big a problem that is in plastic. But nice generous corners, I'll let you look at that and see. You
So I
said,
think the tail doesn't have a fillet added to the.
and fill it there, but, I think it's. I don't think it's unreasonable, like from a structure perspective.
Yeah.
Yeah, obviously, you know, if you can make the whole thing as a nice, you know, molested structure would be ideal. But given the practicalities of fitting things in there, better there than other places.
And my feeling is that it's probably not necessary because
Yeah.
there's so many outside plants like we only need one space that we can put batteries and replace batteries.
Yeah.
That's all.
Yeah.
So it's
What
like
about like servos and things like that? Like, don't those break pretty frequently?
for servos, like I don't know when you place something here, you don't need to have some openings on the fuselage. The whole purpose of the fuselage, main purpose is to carry batteries and all the electronics, and you only need one. Is enough, and we have so many aircraft built in previous methods, only one opening on top is good enough. I mean, I don't know, and you mentioned that it's also for the purpose of some landing gear. I mean, why do you need you assemble landing gear before you put all the fuselage section together? Why do you need to put an opening on top?
Well, okay, for example, the rear landing gear that are in this section, the way the fasteners come is from the top down, so.
Yeah, you assemble them first, and then you put fuselage together.
Yeah, but if the access hatch wasn't there, it would be kind of hard to do.
She's saying.
No, she's saying.
So one of the
This
things,
by
one of
itself.
the reasons why ours was a little bit different is because we had to, because we're doing a push across, we need to continue to access because we're running cabling to get towards the back as well, especially for the power. And then we also have server connections going to the rear. But we'll take that into consideration, but that was.
Yeah,
the
for the
reason-
wires, you do not use such a big opening
Yeah.
for messages. So, and another problem of this field of time, of course, is the weight problem because you have faster and faster the metals. I don't think it's like really necessary to have about the same piece and has and also fastening is like when you consider weight and I'm under concerned about it because in the end all the way add up and your total aircraft weight may become a problem and it cannot take.
That's another concerning part, I think, about putting the two fasteners right around the longerons is you're doubling the fasteners, because then you do, you know, two per.
Well, you don't have to, I mean, you could do it with a single fastener.
And just.
I
move
never
the
used
single
that.
fastener closer to
Yeah.
The longeron.
Yeah, I think I would prefer that to do that.
Okay.
It's not ideal, from a load path perspective to like do it on your side. You can also do it with smart fasteners.
Yeah, also, we did kind of weigh our fasteners and look at pretty much the lowest ones we used in that last week. And
Yeah.
we found it wasn't too bad, but it was under
50
Always the lighter the better,
For
yeah.
all 40.
So I want to say that the first aircraft I made myself didn't some before the first time I did this class, I taught this class. It's a one layer PAA, and for like all the you saw the aircraft and it can fly very well. There was no damage in the so I don't know if it's really necessary to be like, yeah. And also when you talk about, I think you mentioned several times, like the electrical PA has some problem, like structure problem, or the one layer PA, regular PA has some problem, but we did have successful test flights with one layer PA and also with electrical PA. So I personally do not believe electrical PA itself is a problem for making arms airplane. I do not believe one layer PA, regular PA is a problem for making arms airplane. So, well, electrical PA is designed for making arms airplane. And also when you talk about the EFC, and you mentioned that you need that EFC because it's something help like structural reversal. And why do you guys need that?
Well, we had a target and our goal was to do a survey of some application floors. And
Why
Based
do
on
you
the-
need a thrust reversal for our?
When you're landing, because we don't really have good braking and we're coming in, we're targeting 8 to 10 pounds. We want to be able to slow it down once it lands. So it was a feature we wanted to incorporate it, and it's a part of our.
Is there any landing distance requirement?
No, because.
We
ours
never
is
saw
heavier.
that, it kind of certain could be a problem for us.
But it's just something we're addressing because we don't want to overlook it. We're doing a full design, so we also want to address braking. That was.
Whenever you are
application.
making a design unnecessarily complicated, it may cause some problem at the same time.
But it's integrated.
I do
within
not
this-
believe thrust reversal is necessary for our project. That's what I mean. We don't
It's a
have
part of
any
the engineering,
requirement.
Creativity. We're trying to-
Well, let's ask, what compromises did that force on, like, is that
It's,
a heavier system? Is that
it's the same
a-
ESC, it's just, programming a switch on that's all it takes, just programming the switch in the control to enable it. The ESC.
Oh, so there's additional control complexity,
Yeah, just,
but not a trade-off in weight, not a trade-off.
it's the same size.
Maybe more expensive. Yeah, I don't know.
Yeah, I'm thinking it's a little bit more expensive. I'm gonna ask about the expense as well.
I-
as
I placed order last night. It was expensive.
Yeah, $60, $60 ESC.
69.
It's in the range of $60.
Yeah.
They didn't go on the verge.
And in all honesty, we're trying to, we didn't want to just be average. We're trying to exceed. It wasn't, we just didn't
No,
want
no,
to
no,
just.
no,
be
no,
minimum.
not exceed. Let's say I give you a requirement, you optimize for my requirement.
But
This is
we-
what I want, you get over it, I'm not gonna pay for it.
But we just want the plane to stop.
Once your aircraft, most of the time, once your R7 touch ground, you can slow down no matter what, because the friction, everything. Thank you.
Also, what I'll say, briefly to address your concern about lightweight PLA and also regular PLA, we are test printing our fuselage sections with regular PLA. The only reason why I mentioned the problem with regular PLA being an issue with the separation for the single layer was for the wing, just because we were having a lot of issues with the printers dealing with the geometry. And as if we did have some, like for example, we tested one printer. And probably because of the humidity changes or what that was, it wasn't negotiating the specific curvature of that, but that was for the wing. That was with the lightweight PLA. I mean, you saw ours with the single layer, we have no issue. And that was also that like 40% density. And now I think for reference, the black one there is 32 grams per section. The white one with the single layer skin was 14 grams, and now with the double layer, it's 23 grams. So like much more optimized than the other
Yeah.
one. But that was to the wing, not to the design.
Yeah, I know. So the premium, yes, sometimes like different things, different brands. We do have some problem of either or the we just need to like for each type of material, like even different batch of fulfillment we buy
Yeah.
every time, you need to test like
Yeah.
change temperature, change speed, and change everything, change the parameter to make it work. And for you mentioned like some of different pieces together. We did have a solution like they even wrap the fiberglass around. Like there's not much extra weight, but it can make the assembly of different piece much stronger. And also the worst solution I did in previous semester, the one I made, I just rejected it. It worked.
Yeah.
It's not a good solution, but it worked. So I think we can figure out how to make it work.
Yeah, for assembling the pieces, all we did was after we added before adding the carbon fiber was literally just start taping it.
Yeah.
And then with the carbon fiber, that helped with our.
Yeah,
production.
if you use like a whole fabric or cotton fabric, there's no problem
Yeah.
like a 17 piece.
Yeah,
It won't break.
that we
won't.
didn't have it.
If you crash the whole thing, but it won't break.
Yeah. We're also doing lab drawings such as Mark suggested, and our first version of which we're doing has it here. It's like a little fishbone of just a rib with 1 millimeter of peeling.
Yeah.
It's basically gonna do nothing. So we're currently trying to optimize that.
Yeah. So another problem. Okay, who is the pilot of the group? Okay, are you comfortable flying in detail?
Yes.
Okay. Okay.
I
Um,
think it'll be fine.
Are you done?
Yeah.
Okay, that's great. So you had experience before?
No, but just from Mark and I's.
Oh, okay, that's good. I'm just saying that it's gonna be more difficult than a conventional tip. And, you guys mentioned that you want to add LED lights on the airport, why? LED lights, I think you said that.
It's one of the, it's not the definite, but it's the functionality. Normally navigation in airplane, based on the color of the light in each one, navigation, you can tell which direction the thing is going.
No, you don't. We're flagging them. And, we just like, probably when we put like different color tape on the top and bottom, and you can see which direction it is. There's no necessary to make the design overly complicated. Every time you add something, it make it wrong. So here is my requirement. You optimize my requirement. You don't do whatever you want. It's not a fancy development. And the other thing I am not even concerned right now. Well, I will see you probably did a lot of analysis, but I will see in the test flight. But I'm not concerned now. It's a CG. Because right now, I mean, your tail part, because your motor is here. And also because you want mount motor here, you make this one extra thick. So this one is heavy. Here is heavy. And we want to make the CG light around the wing. It might become a problem.
We've discussed moving the wings further back to account for that. If you look at the MQ9 Reaper, which is one of our, not sure how well it shows it in this picture, but if you can see here, the wings are pretty far back, and that accounts for the radar use that that plane has. Obviously, we will not be using radar; we'll be using a cam and a gimbal, but we want to kind of emulate that.
Okay, so my suggestion that we probably can do some this. Find a CG.
Yeah, you can do that.
Yeah, so try to like,
Yeah.
We're trying to like rough Excel calculations more than a CAD. We don't have a
Okay.
full assembly with
Yeah.
like the battery, ESC motor, all that stuff in a CAD. But we have like, Excel with the distance from the nose and the CG.
So you
calculation.
have a spot where you believe your CG is.
Yeah,
Yeah.
we know where our CG should be, obviously with, slight changes in printing and all the weight differences and the fact that we don't necessarily know exactly how much our wings are gonna weigh until we lay them up and weight them.
And then,
It's still a rough calculation.
Also, we're working on the CAD to get every component and we're to see the CG. And we have also put a lot of thought into what you said about the CG being too far back. And the main risk we're gonna mitigate that is moving the wing back. And we do also have a relatively heavy battery that we can kind of step very far forward.
yes, there's a lot of availability for movement to control the CG.
yes, because what happened in the previous semester was that they have the motor and they have a battery push like way like the around the motor. Still they have CG. So well, we'll see in the first test flight. So when will be your first test?
We don't have a target rate yet, but as soon as possible.
We were aiming for the first week.
Okay, good. Hope you will work.
Thank you.
So that's one thing, this whole CG thing, it would be very, very helpful to show on your model, your CAD model, like you showed us your model, where's the CG, where's your believed aerodynamic center and stuff like that. That way, like at least what we're seeing, we can, like, okay, you guys have that in mind. Just because when you show it to us, like we have no idea what that's where you're placing stuff like that. And it would also be helpful in that aspect to show like, okay, the battery's going here. These are camera components, blah, 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 or in this case, you don't have those components at the moment, you place them in weights and say that as well. Motor in the back. That way you get a nice CG, estimate just by looking. I have some other like presentation stuff, and if we are running on time, I don't know.
Standard. I don't know what time we have to be done.
That's like, is that okay with that?
Say 30, 9:30, but it's-
Not to the
there's-
I thought I saw them outside, so
They're just
I have some stuff that we can go over later about more of the stuff. And then some other discussion about some of the stuff.
Thank you.
Thank you.
Good job.
Nice job.
Wait, you guys want to take a picture?
Oh, it's like one.
I was just gonna do the first one.
Yeah.
Let's, yeah, let's not.
You want to move that action? Okay, I guess.
We'll talk about it.
Okay, I'll send you that.
Thank you.
Good evening, thanks to you. I know, I don't even see if you have any questions, but hopefully not.
Oh, Teo, I forgot he was on there.
Yeah, it's all good. Great job. Great job, guys.
Go ahead.
Have the nominal signal diameter, and then these.
Oh, I think he was responding, but I'm gonna log off now, Theo.